Welcome to the video lecture series on digital image processing. Now, the next color model that we will consider is the HSI color model, that is hue, saturation and intensity model. So, as we have mentioned in our last class that both the RGB as well as CMY or CMYK, they are actually hardware oriented. The RGB color model is oriented towards the color display or color monitor. Similarly, CMY or CMYK, these two models are oriented towards color printers. Whereas, when it comes to human interpretation, we said that we don't really think of that given any particular color, how much of red, how much of green and how much of blue is contained within that particular color. But what we really think of is what is the prominent color in that particular specified color. So, which is what is known as hue. Similarly, we have said the saturation, it indicates that how much a pure spectrum color is really diluted by mixing white color to it. So, if you mix white colors to a pure spectrum color in different amounts, what we get is different shades of that particular spectrum color. And as we said that I, the intensity, this actually is the chromatic notion of brightness of black and white image. So, what we have is hue, which tells us that what is the prominent color, prominent primary color or spectrum color in that particular specified color. We have the saturation, which indicates that how much white light has been added to a pure spectrum color to dilute it, and we have this component intensity, which is actually a chromatic notion of the brightness. Okay. Now, the given problem is, given a color in RGB space, can we convert that to HSI space? Now, this HSI model has other importance also in addition to just interpretation by in addition to human interpretation, because you find that this HSI model, it decouples the intensity information from the color information. So, this I gives you the intensity information, whereas H and S, the hue and saturation together, this gives you the chromatic information. So, as we can decouple the chromatic information from the intensity information, many of the image processing algorithms which are developed for black and white images or grayscale images can be applied to this to the images specified in HSI space. So, conversion of an image from the RGB space to HSI space is very, very important. Now, let us see that how we can convert an image specified or a color specified in RGB space to the to a color in the HSI space. Now, in order to do this, what we can do is we can reorient the RGB cube, the RGB space in such a way that the black point or the origin in the RGB cube is kept at the bottom and the white comes directly above it. So, as shown here. So, we find that it is the same RGB cube, and what we have done is we have simply reoriented this RGB color cube, so that the black comes at the bottom. So, this is the black one, the black comes at the bottom and the white comes directly above this black point. So, naturally, as before, the line joining black and white, this represents the intensity axis, okay, which So, any point on this particular line which joins black and white, they won't show any color information, but they will have different intensities or different gray shades. Now, once we reorient this RGB cube like this, now suppose we have a color point, we have any color point specified within this RGB cube. So, I have this color point specified in the RGB space. Now, for this color point, now our aim is how we can convert this RGB specification into HSI specification. So, as we said that the line joining black and white, this line is the intensity axis. So, in the HSI space, I can very easily compute the intensity component, because for this point, say I say this is a point say x, I can represent this point as a vector joining from black to this particular point, and the intensity component that is associated with this RGB value is nothing but projection of this vector on the intensity axis. So, if I project this vector on the intensity axis, then the length of this projection tells us what is the intensity component associated with this particular RGB specified color point. Okay. Now, to get this, what I can do is we can draw a plane, we can just pass a plane which is perpendicular to the intensity axis and containing this particular point x. So, the point at which this plane will cut the intensity axis, that point represents the intensity associated with the RGB component specified for this particular point x. So, this is how we can compute the intensity component. And then you find the next component, that is the saturation. How we can compute? So, this one tells us that what is the intensity. Now, how can we compute the saturation? Because the line joining black and white, the intensity axis, any point on the intensity axis has only gray shades, this does not have any color component. So, you can say that the saturation of all the RGB points, the saturation associated with all the RGB points lying on this intensity axis is equal to 0, and the saturation will increase as the point will move away from this intensity axis. So, keeping that in mind, we can say the distance of this point x from this intensity axis, this distance tells us that what is the saturation that is associated with the RGB components of point x. So, you can very easily compute the intensity and saturation corresponding to any RGB point given in the RGB space. Now, the next question is computation of the hue component. So, out of hue, saturation and intensity, we have been able to compute the saturation and intensity very easily. The next component which is left is the hue component. Now, for hue component computation, the concept is slightly more complicated. Now, we find that in this diagram, we have shown a plane passing through the points black, white and cyan. So, as we said that the line joining black and white is the intensity axis. So, intensity at point black is equal to 0 and intensity at point white is maximum, that is equal to 1. And the other point which defines this particular plane is the cyan, that is this particular point. Now, you will appreciate that for any points in this particular plane defined by these 3 points black, white and cyan will have the same hue, because as we said that hue indicates that what is the prominent wavelength of light present in any particular color. And from our earlier discussion, you can also very easily verify that for any point given on this particular plane defined by these 3 points cyan, white and black, for any points the color components can be specified by linear combination of these 3 points cyan, white and black. Now, because white is a balanced color which contains all the primary components in equal proportion and black does not contain any color component, so these 2 points white and black cannot contribute to the hue component associated with this point line in this plane. So, the only point which can contribute to the hue component is the cyan. So, for all the points lying in this plane, the hue will be same and it will be same as the hue associated with this point cyan. So, here you find that if I rotate this particular plane around this black and around the intensity axis by an angle of 360 degree, then I will trace all the possible points that can be specified in the RGB color space. And by rotating this plane by 360 degree around the intensity axis, I can generate all possible hues that can be all possible hues corresponding to every possible RGB point in the RGB color cube. Now, in order to do that, what we do is like this. Suppose I take projection of this RGB cube on a plane which is perpendicular to the intensity axis. So, if I take the projection, then the different vertices of the cube will be projected on a hexagon as shown in this particular figure. So, the 2 vertices corresponding to red and black, they will be projected at the center of the hexagon. So, this point will be the projected point for both white and black. And the other primary colors of light and the primary colors of pigments, they will be projected at different vertices of the hexagon. So, here you find that if I draw a vector or if I draw lines joining the center of the hexagon to all the vertices of the hexagon, then red and green, they will be separated by an angle of 120 degree. Similarly, green and blue, they will be separated by an angle of 120 degree. Similarly, blue and red, they will also be separated by an angle of 120 degree. In the same manner, for the secondary colors, yellow and cyan, they will be separated by an angle of 120 degree. Cyan and magenta will be separated by an angle of 120 degree, and similarly magenta and yellow, they will also be separated by an angle of 120 degree. However, the angular separation between red and yellow, this is equal to 60 degree. So, if I take the projection of the RGB cube on a plane which is perpendicular to the intensity axis, then this is how the projection is going to look like. Now, along with this, you will find that the projection of the shaded plane that we have seen in our previous slide will be a straight line like this. So, for any point specified in the RGB color space, there will be a corresponding point in our projected plane. Say this is a plane corresponding to a color point in the RGB color space, and the plane on which this color point will lie, the plane defined by the corresponding color point, the black point and white point on which this point will lie, that will be projected as a straight line on this particular plane. So, as we rotate the plane by 360 degree around the intensity axis, this particular straight line will also be rotated by an angle of 360 degree around the center of the hexagon, So, if I rotate this particular shaded plane by an angle of 360 degree around this black and white axis of the intensity axis, its projection onto the plane, onto this perpendicular plane, which is a straight line, will also be rotated by an angle of 360 degree around the center of this hexagon. Now, this gives us a hint that how we can find out the hue associated with a particular color point specified in the RGB color space. So, the hue can be computed like this, that the straight line, it is the angle between the straight line, which is the projection of this shaded plane with one of the primary colors, and normally this primary color is taken to be red. And this angle is normally measured in anti-clockwise direction. So, using this particular convention, the red will have a hue which is given by 0 degree, and as we rotate this shaded plane around this intensity axis, this particular straight line, which is the projection of it, will also be rotated by 360 degree, and as it is rotated, the hue is going to be increased. So, hue is normally measured by the angle between the red axis and the line which is the projection of this plane on this projection of this shaded plane on this plane of this hexagon. Now, given these particular concepts, that is how we can obtain the hue, saturation and intensity components for any color specified in RGB color space. Now, we can find out that if you follow the geometry of this particular formulation, then we can have very easy relations to compute the H, S and I components from the R, G and B components. So, here the hue component, the H will be simply given by an angle theta, and as we said that this theta is measured anti-clockwise from the direction of red. So, this will be equal to theta if the blue component is less than or equal to green component, and it will be 360 degree minus theta if blue component is greater than the green component. So, this is how we can compute the hue component in the HSI specific in the HSI model, where the value of theta is given by cosine inverse half of R minus G plus R minus B divided by R minus G square plus R minus B into G minus B, this to the power half, where R is the red component, G is the green component and B is the blue component of the color specified in the RGB space. So, from this R, G and B component, we can compute the value of theta following this expression, and from this theta we can find out the hue component in the HSI space, as hue will be equal to theta if blue component is less than or equal to green component, and hue will be equal to 360 degree minus theta if blue component is greater than green component. Similarly, following the same geometry, we can find out that the saturation is given by 1 minus 3 divided by R plus G plus B into minimum of R, G and B, and the intensity is simply given by 1/3 into R plus G plus B. So, from this red, green and blue components, we can very easily find out the hue, saturation and intensity components. So, as we have converted from RGB space to the HSI space, similarly, we should also be convert any color specified in HSI space into the components in the RGB space. So, to do that conversion or the inverse conversion, the corresponding expressions can be found as, you find that whenever we want to convert from HSI to RGB, then there are three regions of interest. One region is called RG region, and in RG region, H lies between 0 degree and 120 degree. The other region is called GB region, and in GB region, H lies between 120 degree and 240 degree. And the third region is called BR region, and in BR region H lies between 240 degree and 360 degree. And here in the RG region, you find that getting red, green and blue components is very easy. What we do is simply the blue component is given by I into 1 minus S, where I is the intensity and S is the saturation. The red component is given by I into 1 plus S cosine H divided by cosine 60 degree minus H, and green component is simply given by 1 minus R plus B. Similarly, in the GB region, the first operation that we have to do is we have to modify H. So, we have to make H is equal to H minus 120 degree. And once we do this, we get the RG and B components like this. R is equal to I into 1 minus S. G is given by I into 1 plus S cosine H divided by cosine 60 degree minus H, and blue in the same manner is given by 1 minus R plus G. And in the third sector, that is in the BR region, we have to modify first H like this. H should be equal to H minus 240 degree. And once we do this modification, then the G component is given by I into 1 minus S. The blue component is given by I into 1 plus S cosine H divided by cosine 60 degree minus H, and obviously the R component is given by 1 minus G plus B. So, you find that using these simple expressions, we can convert a color specified in the RGB space to a color in the color components in the HSI space. Similarly, a color specified in the HSI space can be easily converted to color components in the RGB space. So, here in this diagram we have shown the effects of this different components H, S and I on the colors. So, in the first row you find that the first rectangle is a color for which hue is equal to 0, intensity is equal to 128 and saturation is equal to 255. So, as we said that our hue is measured from the red axis, from the red line. So, hue equal to 0 indicates that it is red color. In this case, the saturation equal to 255, which is the maximum, that means it is the pure red color, and intensity here is 128. So, for other rectangles in the same row, what we have done is we have kept hue and intensity constant, whereas the saturation is decreased. So, here you find that as we move from left to right, it appears that this red has becoming milky gradually. So, as we have saturation is equal to 200, which is less than 255, it appears that some amount of white light has been added in this particular red component, and that is very, very prominent when S is equal to 100 or even S is equal to 50, where a large amount of white light has been added in this red component. In the second row, what we have done is we have kept hue and saturation constant, that is hue equal to 0 and saturation equal to 255, and what we have varied is the intensity component or the I component. So, here you find that as we decrease the I component, the different rectangles still show the red color. As we move from left to right in the second row, they are still red, but the intensity of the red goes on decreasing. So, if you just note the difference between the first row and the second row, in the first row it appears that some white light has been mixed with the red, whereas in the second row there is no such appearance of mixing of white light, but it is the intensity which is being decreased. If you look at the third row, in the third row what you have done is we have kept the intensity and saturation constant, but it is the hue component which has been changed. So, we have started with hue equal to 0, which is red, and here you really find that as we change the hue component, it is really the color which gets changed. Unlike the previous two rows, in the first row it is the saturation or more and more white light is being added to the pure color. In the second row the intensity is getting changed, but in the third row, where keeping the intensity and saturation same, we change the hue component, it is the color itself that gets equal to changed. So, here you find that when we have hue is equal to 100, it is the green color. When we have hue equal to 150, it is the blue color, whereas when hue is equal to 50, it is a color between yellow and green. So, with this we have introduced the various color models, we have introduced the RGB color space, we have introduced the CMY or cyan, magenta and yellow color space, and also CMYK, that is cyan, magenta, yellow and black color space, and we have also introduced the HSI color space. And we have seen that given any color, given the specification of any color in any of the spaces, we can convert from one space to another. That is, from RGB to CMY, the conversion is very easy. We can also convert from RGB to HSI, where the conversion is slightly more complicated. Now, with this introduction of the color spaces, next what we will talk about is the color image processing. So far what we have discussed is the representation of a color or the representation, and when you take an image and take the colors component, the colors present in the image, then so far we have discussed how to represent those colors in either the RGB plane or CMY or CMYK space or the HSI space. And the images represented in any of these models can be processed. So in color image processing, we basically have two types of processing. One kind of processing is called pseudocolor processing, this is also sometimes known as false color, and the other kind of processing is what is called full color processing. In pseudocolor processing, as the name implies, that these colors are not the real colors of the image, but we try to assign different colors to different intensity values. So pseudocolor processing, actually what it does is it assigns colors to different ranges of gray values based on certain criteria. Now, what is the purpose of assigning colors to different ranges of gray values? As we have mentioned earlier, that if we have a simply black and white image, we can distinguish hardly 2 dozens of the gray shades, whereas in color we can distinguish thousands of color shades. So, given a grayscale image or an simply black and white image, if we can assign different colors to different ranges of gray values, then the interpretation of different ranges of gray values is much more easier in those pseudo-colored images than in the grayscale images. So, we will discuss about how we can go for pseudo-coloring of an image given in the pseudo-coloring of a black and white image. So, as we said that this coloring has to be done following some criteria. So, with this introduction, and of course, in case of full color processing, as the name indicates, the images are represented in full color and the processing will also be done in the full color domain. So, given this introduction of the color processing techniques, the two types of color processing, pseudo color processing and full color image processing, we finish our lecture today. Thank you.